Welcome to our lesson on the quadratic function. So to start with, a quadratic function is anything that's in the form y equals ax squared plus bx plus c. The only restriction on that is that a cannot be 0, because what makes this a quadratic function is that we've got an x squared in there. An x squared is our highest power, which means that we're going to end up with a curve when we graph this rather than a straight line. But if we go and make a 0, so if we make it y equals 0x squared plus 5x minus 3, that's actually not a quadratic function anymore. That doesn't give a curve, that gives a straight line when we graph it. So a cannot be 0. But b or c could be 0, and that's absolutely fine. Like the most basic example of a quadratic function, y equals x squared. Well, that's where b is 0 and c is 0. And that's absolutely fine. That's a quadratic function. We can do a few different things with that, and we'll have a look at those as we go through. First thing, the concavity of a quadratic function. It's really got to do with when we start to graph that as well. It's determined by the sign of a. Now, what that means is if a is positive, if a is 1 or a half or 3, or any other positive number, it means the curve is concave up. Concave up looking something like this. Now, it could be steeper, it could be wider, but that's fine. This is concave up. It's a U-shape for up. Concave down, the opposite is if a is a negative number. So if you've got y equals minus 5x squared, it doesn't matter if you've got minus 5x squared plus 3x plus 2. It's not how many negatives there are, it's whether a is negative or positive. So the U-shape is upward and the upside down U-shape is downward. As a becomes larger, the curve becomes steeper and vice versa. So 2x squared or 3x squared might look like this, but a half x squared might look like this. We'll look at those as we do some examples through this. But the value of a really is important here. The value of c, that number that's at the end by itself that doesn't have x with it, is the y-intercept. Okay, now any parabola always has a y-intercept. Okay, any parabola always has a y-intercept. Now, a parabola may have 1, 2, or 0 x-intercepts. The y-intercept, of course, is where our curve hits the y-axis. The x-intercept is where the curve hits the x-axis. So it could have maybe 0, 1, or 2 x-intercepts, but it always has a y-intercept. When we graph a quadratic function, that's called a parabola. It's not called a parabola. It's called a parabola. That's just me being a little bit silly there, but it is a parabola, not a parabola. And every parabola has a turning point. Okay, if the curve is concave up, if it's facing upward, the U shape, then that has a minimum turning point. It means there's a point where we can't go any lower on that curve. Conversely, if it's concave down, the turning point is a maximum. So any parabola always has what we call concavity. It always has a y-intercept, and it always has a turning point. It may or may not have x-intercepts, but it always has those couple of features there that I've mentioned. Having a look at a couple of graphs here for y equals x squared, I'm going to do a table of values. I'm not actually going to write it down. I'm going to talk about it as we're doing it. So if I've got y equals x squared, I'm going to go from negative 3 up to positive 3. I'm actually going to start in the middle there at 0. So if I've got 0 squared, well, I end up with 0. Okay, so that means my curve passes through the origin. Its y-intercept is 0, which makes sense, right? Because if we look at what number is at the end here by itself plus c, well, c is 0. Okay, which makes sense that this curve passes through the origin. If I go and choose x equals 1, 1 squared is 1. Now if I take 2 squared, I get 4, and 3 squared is 9. I'm taking an approximation of these points. But if you went to go use Desmos, you could find actually the exact shape of what this looks like. Now, when we go into the negative values here, the mistake that people often make when they graph these is to do something like this. They say, well, minus 1 squared, that's minus 1. And minus 2 squared, well, that's minus 4. Minus 3 squared is minus 9. No. The positives won't change there. Okay, but squaring a number makes it positive. A negative multiplied by a negative gives me a positive. Negative 2 multiplied by negative 2 gives me positive 4, not negative 4. So what I end up with this here is actually a reflection. Okay, a reflection or an axis of symmetry in my curve, and any parabola always has an axis of symmetry. Okay, it's always through that turning point. It was one of the points on the last slide there. Wherever that turning point is, there is always going to be an axis of symmetry. And a curve looks something like this. Okay. Now, please make it look like a curve. It's not a V. Okay, it's not two straight lines joined together. It's a curve, so it should look curved. And if you did draw that on a set of graph paper, you would find that it actually is a curve shape, and it starts off quite flat and then gets very steep. Now, if we went all the way up to x equals 20 here, we would almost have a vertical line because it would be moving upwards so quickly. Let's have a look at our next one. I've got minus x squared plus 5. A couple of things to note already for me here. I've got a y-intercept of 5. Okay, because at x equals 0, I'm going to have 5. 5 is that constant term that has no x associated with it. That's my y-intercept. So I've got 5 here. Now, if I go start putting in some values, I'm going to find that what I've actually got in front of my x squared here is a negative, which means I'm talking about my curve being concave down. Okay. Now, that's not the same as the previous example where I said minus 1 times minus 1 gives me positive 1, or minus 2 times minus 2 gives me positive 4. What we're talking about here is a negative in front of our square number. So minus 1 times minus 1 still gives me 1, but then when I've got a negative in front of that, it's actually 3 negatives. It's a triple negative if you'd like. So let's start with our positive numbers because they're a little bit simpler. And what we see here is if I've got 1 squared, I get 1. And if I've got minus 1 plus 5, or the other way I could write this curve is y equals 5 minus x squared. They mean exactly the same thing because I've got plus 5 as my constant term and minus x squared. So I'd end up with this 0.14. When x equals 2, 2 squared gives me 4, so I've got 2, 1. At x equals 3, I end up at negative 4. And we've got our curve there. Now, similar to our last example, if I go put in the exact same numbers but they are negative, I'm going to end up with at negative 1, I'll be at 4. At negative 2, I'll be at 1. And at negative 3, we'll find ourselves down at negative 4. Behaves in the exact same way. Again, that axis of symmetry is happening through that turning point, and it does happen to be where the y-intercept is as well. It doesn't always happen that way. Our next example, it won't happen that way, but any parabola always does have an axis of symmetry and a turning point. Here we've got y equals x squared minus 5x plus 6. I'm going to use a table of values between minus 1 and positive 5 here, only because I know those numbers are going to give me a good shape. It's also going to include my turning point as well. A couple of things I notice here straight away. I've got A is greater than 0, which means I'm concave up. I've got a y-intercept of 6. My constant value, my number that's by itself is positive 6. That's helpful. And then I've got a negative 5x in between there. So let's have a look at what this looks like. I'm going to type into my calculator each of these values, making sure that I type it in exactly like this. Y equals minus 1 squared minus 5 times minus 1 plus 6. Type it in that way, brackets around the values you're putting in, especially when those values are negative. You will end up much more likely to having this correct, and it won't be a calculator problem if it is incorrect. But if you forget to put those brackets around, your minus 1 squared will stay as negative 1, not become positive 1. For that value, I end up with 11, somewhere up here. Now, when x equals 0, I can go straight away and just say that's 6, because that's my y-intercept. When x equals 1, I go and substitute that. I end up with 2. Now, something interesting happens here when I go and put in x equals 2. I end up with 4 plus 6 minus 10, which is actually 0. So I've found one of my 2 points there where I have an x-intercept. Now, the exact same thing happens here when I have 9 minus 15 plus 6. That gives me 0. So what's going to happen somewhere in here is we're going to have our turning point. We don't have the exact coordinate of our turning point yet, but we will shortly. Now, when I go and substitute in x equals 4, I end up with 2. 16 minus 20 plus 6 is 2. And when I do the same thing with 5, I end up with 6. Now, I hope you can see that there's definitely a symmetry happening with these points. And the symmetry is happening in this line here. The last couple of examples, it was happening on one of the two axes. But here it's happening in that line there. That's our axis of symmetry of this parabola. So if I go and have a look at what this curve looks like, good enough for my writing there on the right hand side, I could go and extend those out so they are the same size. We could go put in a value for x equals 6 and we'd find it would be the same y value as when x equals -1. They are symmetrical after all. Now to find this turning point down here, it is a minimum turning point. Okay, it is a minimum turning point because we have a curve that is concave up. Now that minimum turning point is going to be halfway between those two x-intercepts. So if I take halfway between the average of 2 plus 3, it's going to be at x equals 2 plus 3 over 2, which is 2.5. If I substitute 2.5 into my equation, I end up with negative 0.25. So that's the coordinates of my turning point there. My turning point happens at 2.5, negative 0.25. Okay, so that's how we would go and find the coordinates of that turning point. We take halfway between the two x-intercepts, or we find where the symmetry is happening. So if we want to go find where the symmetry is, in fact, we can take halfway between any two symmetrical points if you like as well. We noted that these ones produce the same y values as well. So if we wanted to say 4 plus 1 over 2, or we could say 5 and 0 produce the same values. Okay, 5 plus 0 over 2 is also 2.5. So the reason that this curve has symmetry is because those when x values are the same distance away from the line of symmetry, the y values will be the same. I hope this has been helpful and you're able to now recognize some features and graph a quadratic function.